Right, great. So the next talk is by Victor.
Yes, so hello everyone. Today I'm going to talk about clustering with bandit feedback with the very fancy subtitle breaking down the computation information gap. So I will try to explain why we present this subtitle. So it's a joint work with my two PhD supervisors, Nicolas Verzelen and Alexandra Carpentier from Potsdam and Montpellier, and also with a colleague from Université. So for the presentation, I will start by giving the setting and then giving benchmark and finally our main results and explaining our theorem and method. So for the setting, so we consider a bandit problem where we can collect actively and sequentially data from a bandit with n arms. And for each arm, there is a probability distribution associated to this arm. So for the presentation, I assume that this probability distribution is Gaussian. In the paper, it's sub-Gaussian. And each arm in particular is associated to the mean vector of this probability distribution called mu A. So let's observe that here we consider d-dimensional feedback in our model, which is kind of different from the most common literature on bandits. And usually in this kind of bandit setting, at each time, what we call sequentially inactively is that the algorithm is able to choose one arm based on all past observation, and it receives the data which follows the probability distribution associated to the chosen arm. So if we just give a small picture, we have five arms, and at each time we can choose one arm and get a sample from the probability distribution associated to this chosen arm. And in particular, we are able to sample multiple times the same arm, and we can focus the budget on some important arms, some relevant arms, and subsample more on these important arms. And in our problem, we assume that there is some structure over the set of arms, and we want to recover this structure, and this structure is a clustering. So we assume that there is an hidden partition of the arms, and two arms within the same group share the same mean vector, so share the same probability distribution. And we assume that there is k groups, and k is known, the number of clusters. So if you get only one data from each arm, it's a usual Gaussian mixture model for clustering. But in our problem, we can get multiple data from the same probability distribution, so it's a bit different. And the objective is to recover this unknown partition G star. And as usual in bandit theory, the second objective is to minimize the number of observations that we will need, as it is costly to get data. So for that, we sample arms until some time t, and at the end, we have to output some estimation of the hidden partition. So this is the picture. Imagine that, in fact, the two first arms are in the same group. They share the same probability distribution. The third one is alone, and the last two ones are in another group. And in fact, we don't know the different centers of the groups that I labeled as lambda. And we want to, based on the observation of data points, we want to recover this unknown partition. So the groups are non-empty in this joint. And just for the presentation, to have something clearer, I will assume for this presentation that all the groups have roughly the same size. So they all have the same number of arms in each group. And we focus on the delta pack setting. So you already saw some of this setting in the previous talks. So we are given some prescribed probability small delta. And given this probability error, we have to recover the exact partition with a probability of error smaller than delta. And the problem, as usual in clustering, is defined only up to permutation of the groups. It's not, if we give some label to one group, it's not a problem. We just have to relabel in a way that it's exact. And our main contribution is in considering this problem in some kind of with a parameter which corresponds to how hard it is to cluster in this setting, and it's the minimal gap which drives the hardness of the problem, which is the smallest distance between two centers of the groups, and this parameter is important for the story that I will tell. So I'll continue with a benchmark and with the lower bound. So our main contribution is in showing that this budget T star, which is in my slide, is really an important quantity for the problem. So it comes with three terms. The black one, the n, it just tells that we need to sample at least once each arm. And so let's not focus on this one, but the blue and the red terms are interesting. We have a first term in blue, which doesn't depend on the dimension of the problem. It only depends on the number of arms. And it appears as quite usual in classification, even in supervised classification. In a Gaussian setting, if you want to test if you are in one Gaussian with one mean or another Gaussian with another mean, we'll have to pay 1 over delta square at least. So that's the first term, and you have to do that for each arm. So that's why you have the n over delta square term. And in our paper, the interesting part is that we show a second order term, which depends on the dimensionality of the problem. It depends on the dimension. And we prove exactly a tight term depending on this dimension on what we have to pay to solve our problem. So in some sense, this term, scaling with the square root of d, it shows that for our problem, we need at least to estimate the centers of the group to some extent in order to be able to recover the clustering. Even if it's not the true objective, in fact, we could just don't care about the centers of the group, while we still have to estimate at some extent, and this is the scale at which we have to estimate it. So we provide, as a first result, a lower bound, saying that any delta pack algorithm will have to pay at least this budget up to a constant on at least one environment for which the minimal gap is delta, is capital delta. And so just to continue describing this optimal budget T star, we have a first term, I said, which is some kind of a supervised learning classification budget. But it's also the term that appears as asymptotic, where delta goes, small delta, the probability of error goes to 0. Then there is a paper from Yang and al. Which show that with an optimal numerical constant, they obtain the budget that you need to cluster with bandit feedback, and it is exactly the first order term. So the blue term, when delta goes to 0, my second order term in red is negligible, and you already you don't see the dimensionality of the problem in the asymptotic regime. And our contribution was to show the dimensionality of the problem in a non-asymptotic regime where delta is not necessarily asymptotically small. And the second benchmark that I wanted to talk about is uniform sampling. So it's just to compare the problem to a supervised learning to a non-supervised learning problem in the batch setting. So imagine that you sample each arm the same number of times. Then some good statistic would be to just consider the empirical mean of each arm and to cluster with a batch clustering, for example, k-means or something like that, the mean of the arms. Well, the empirical mean of the arms. And in this case, it was proven that there is in fact a computational gap between what is best achievable with an algorithm, maybe not computationally possible, and what is best achievable with a polynomial time algorithm. And here, in black, we show that if we want an algorithm to be a 1 over n pack, we need at least the black term, which is exactly my T star, my budget that I gave to you. But we have also an extra term in red, which actually is necessary. It can be achieved with an algorithm, with a polynomial algorithm, and we can't do better with a polynomial time algorithm. And this is what is called the information computation gap. And the story of my presentation today is that, in fact, in active learning, in the active setting, you don't pay this gap. So this is the next part, talking about the upper bound and our method. So very shortly, we provide an upper bound for this problem. So for that, we construct an algorithm as a two-step procedure. So first, we try to identify one representative from each group of arms. So we just need to take sequentially arms and to decide if they are already in a group that was represented in my set or not. And we perform a series of two-sample testing tests. And we can estimate this set of representatives. And when we have exactly one arm from each cluster, we can focus the budget on these clusters, on these representatives to estimate the centers, instead of having to estimate the centers at the same time as classifying. So next, we will estimate the centers with a budget with roughly T star over K. And the other arms, which are not representatives, will use T star over N. And based on a distance-based classifier, we will be able to classify the arms with a budget which scales as T star. Okay. So as an upper bound, we prove that in the balance case, where all the groups are roughly the same size, our algorithm in expectation will reach up to a constant this optimal budget T star. And we performed numerical experiments showing that when K is large enough, in fact, we can do better than uniform sampling. So just for to have something, Oracle book means uniform sampling, just to connect with the literature that we use this name. And so the take-home message is that we answer the three following questions. Can we improve the budget of a simple uniform sampling strategy? Can we achieve optimality for a problem? And is there a computational information gap? And so for the first question, we answer yes. The algorithm that we provide outperforms uniform sampling when K is large enough. We also achieve optimality, and we show that this term T star drives exactly the hardness of our problem. And finally, our algorithm is computationally efficient. It's actually a polynomial time algorithm. So we prove that we can achieve the optimal bound with an efficient algorithm, contrary to the batch setting. So I thank you for it.
So what is the challenge to get this result also in the balance setting, or is it not possible?
If we are not in the balance setting, so in the paper actually we consider the unbalanced setting just for the So it's tight if the groups are not really
Can you hope for anything in case you don't know K, the number of clusters, beforehand?
Actually, our method could work if we know an upper bound on K.